For these, I'm not entirely sure if these are the equations that were in the slides, because I know this one was. Not sure what the other one was, but I think it was maybe that the flow rate is velocity times area. I could be wrong, but that is what I've written here. And I also just recorded this section and then realized I didn't press record. So, that's real fun. Anyway, I was going over explaining why I'm drawing triangles here instead of just drawing the formulas. It's how I was taught in grade 11, and my brain still thinks this way. Literally what these triangles mean is if I'm looking for Q, I cover Q with my finger, I know it's V over T. If I'm looking for V, I cover it with my finger, I know it's Q times T. If I'm looking for T, I cover it with my finger, I know it's V over Q. It's the same as just saying, okay, V equals QT. That is literally what this triangle is. It's just taking this and just making it different. You can use the triangles, you can just remember the equation V equals QT and Q equals small va. So here this is confusing. I think this is referring to the volume. It is confusing because there's a lot of V's, okay? But I'm pretty sure it is because this is in italics. I wrote this a month ago? I don't remember. Can't remember what I was thinking at that specific time in time and area in space. But yeah, okay. What I assume it is the velocity, the volume is equal to the flow rate times the time. Or what makes more sense is the flow rate is literally the volume over the time. That makes sense to me. Because the dimensions are meters 3 per second. So volume, time. Okay? So that's the one thing you should know. That the flow rate is volume over time. The other formula that you should know is that the flow rate is equal to the velocity times the area. So the notation you're probably used to is this, right? Equals V over T, although this is a capital V, I'm just drawing it like a cursive, but use the Q notation. But yeah, again, the Q notation I don't like because in heat transfer, Q is heat, so it's confusing. But for now, it is the flow rate, okay? Now, when we talk about the volume, we're talking about the total volume. So that's for the casting and the feeder. So the time to fill everything is the volume of the casting and the volume of the feeders. That's the little sub-formulas you need to know, okay? Then the velocity of the sprue exit, no, the volume of the sprue exit. That makes more sense. Okay, yeah, velocity of the sprue exit, okay, velocity. If I'm incorrect, please correct me. It's just, again, it's been a while, but I'm pretty sure it's velocity, is equal to the square root of 2gh. H is the effective height of the molten metal head in the sprue. Okay, so the sprue is this thing that comes down, right? The feeder. That then goes into the runner, and then the casting, and then the riser. Okay, this is our sprue. This is our sprue exit, or the sprue exit is here somewhere before the gate. So the velocity of our sprue exit is the square root of 2 times g times h. And the height we're talking to is this one, that effective height. Okay. If the area that we get at some point is weird, change the time to fill and just iterate until you get a proper area. Okay, so for this section, it might just be best to look through past exam questions. I'm going to scroll and show you what we have. In this past question, where they ask you to design, no, not design, where's the other question? We can eat, sketch, calculate. Yeah, okay, here. Calculate the dimensions of the risers using a feeder efficiency of 20%. estimating your cavity dimensions. So this is the question. The parts about the volumes we haven't gotten to yet. I'll get to that in a moment. But what the part we have got to already is the modulus. So here you can see them calculating the modulus, and then using that to find the diameter and length needed. Like we said, you're going to sub into that formula that we had over here. Yeah. So like I said, these are our relations we have. And you know that for a cylinder, you have the cylinder formula for area and was it volume, velocity, volume, yeah, of volume. And then you literally just sub in, you plug and play until you can calculate the unknown. Here again, we have calculations where we find the modulus. We sub in the volume of the cylinder over the area of the cylinder. So literally what we said before. And then we can find the riser diameter with this D. And then this is subbing into our VF equation. But I'm going to go into these in a moment. I just want to show you the previous calculations we did. Here are more modulus calculations from a past question paper for this one. Okay. So in this case, we get our sprue dimensions for sprue exit. Like we said here, it's Q of velocity. So I know I got a bit stumbled up on which V was which, but it was Q A V. Okay. Where Q is area times velocity. Okay, that's the thing you need to know. So I apologize for me stumbling over it, but here is an equation. And then just, we also have this over here, being the speed, velocity of the sprue exit. Although here they have in millimeters per second. And then you can always just sub for the unknowns. So it's just literally those few equations that we had. You plug and play, find the unknowns, and it usually ends with the diameter. Okay? And that is literally the extent to which that particular part was asked. In terms of time to fill, not asked a lot, but for example, here it is, where you have the flow rate, you have the volume and the time to fill, and then you can find the flow rate. You use the flow rate to find the area at the sprue exit, and then as soon as you have the area, you can sub it into your thing where you have the area of a volume, that equation that we had with the modulus and stuff. I think it's that one, but you kind of work your way to the diameter. If you're not sure what to do in the exam, just write down those relations we saw, those equations we went through, and just solve those equations and see what unknowns you have and try to find those unknowns. Literally, that's how I approach a lot of the exam questions, where I'm working at the exam question for 20 minutes and then I actually ask myself, what was I working out again? Oh yeah, okay. Oh, I see I'm halfway to the answer to that already, and then I answer the question. Yeah, I'm just seeing here again. They give you filling time, the flow area ratio. And then you can actually just calculate all the other unknowns. So work through these past questions. It'd be very good practice, because this is basically all the ways it can be asked. I'm just going to go through the one last type of calculation they can ask you. This is volume and area calculations for the feeder. Okay. I just want to make note again of what alpha is. Alpha is the shrinkage fraction. And I've scrolled up here, and the shrinkage fraction is equal to the percentage change in volume, because our metal part is always going to be shrinking. Okay. And that percentage change in volume is usually 3.16%. So important to memorize this value, 3.16, and that is alpha. So for the volume and area calculations, it helps to understand what is happening when we're pouring the metal into when we're pouring our metal into our entire process. So firstly, we pour the metal into our feeder, okay? There's our feeder. Actually, just make me like this little dam thing. I still don't know what this is called. I'm going to remember tomorrow, but it's right now I can't remember what it's called. This part, you know, that dips. But anyway, we have that part, the feeder, and runner part, and then we have the cavity and the riser, okay? It's a very simple thing. This is a horrendous feeder, okay? Anyway, you are pouring the metal, well, you're actually pouring it in here, and it's turbulence, and then it's going in here, but just for the fact of simplicity, just imagine we're pouring it directly into the feeder, or rather we're only consider the velocity at which it's entering the feeder. It's going to be roughly the same as the velocity we pour here. I'm just thinking in terms of you're wondering, but technically there's turbulence here, and that's not going to be exactly the same as the volume here. But for all intents and purposes, just imagine simply metal enter here, okay? The metal that's poured into the feeder here at the feeder is associated with the velocity VF. Ugh, not velocity, volume. All these V's, okay. In the exam, it really would help if you write cursive V's for volume and just normal V's for velocity or small V's. But it is confusing, man. Anyway, so the volume of the feeder, the volume that goes into the feeder undergoes some shrinkage, okay? That's why we subtract the shrinkage factor times this volume of the feeder. So if you're with me so far, the volume of the feeder is equal to, or whatever, but not the volume of the feeder, but sorry, no. What happens is the volume of the feeder gets minus alpha VF. That is the amount that it shrinks by. And that makes sense. The change in volume, which is alpha, is being multiplied by VF. So yeah, that is subtracted. Then it goes into the cavity, okay? And here, it also undergoes shrinkage. It undergoes shrinkage by alpha times VC. VC being the volume of the cavity, okay? And once we have everything minus, it apparently equals 0. But this is just to understand the process. I'm going to go into what it means the most.